Okay, so we've done the pre-processing for the tire and we're now ready to run the EDEM PM FlexTire coupled simulation. I've set up a working directory where I've copied in the clay1_6x2 meter simulation deck, and those files are coming from the PM FlexTire example, along with the tractor tire step and tractor rim step. The tractor tire step was processed with the batch mesh file here, calling the step to obj file, pointing to the mesh configuration file and passing the step. Leveraging hypermesh, I've adjusted the tolerance to quantify the bead elements as 5% of the radius. Max to min element length is 50 to 30 millimeters. D belt was set at 80% of the diameter of the tire, and we've offset the tire 1200 millimeters in the Z and rotated the tire 90 degrees in the second input element. After running that mesh bat, we got the output files that we need, which include the .off files, sidewall, inside, belt, and bead, and the obj file that will import into EDEM. The BDF file was also generated. Before I switch over to EDEM, I'll also point out that I've already updated the tractor tire.flextire file with the appropriate inputs, specifying units of millimeters, degrees, newtons, kilograms, and seconds. In the solver, I've got the recalc normals to be 0.05 seconds. So that is the frequency at which the normals are recalculated for the tire. And I have the output selected as 01. That means that while the simulation is running, the PM FlexTire solver will output at a frequency of 0.01 seconds. What I have updated in this file already is the path that points to the required input files. So the location of the step file, the FTX file, and the .off files, bead, inside, and belt have been updated, along with a BDF and OBJ file. I'm going to switch over to EDEM and point out that if I open up this tire model, and I've already got a tire in here, and this was set up to demonstrate how to define the motion of the tire. So I'm going to replace this geometry with CAD and select the tractor_tire.obj. I'll import that with units of millimeters. And we can see that we now have our tire model imported, and it looks appropriate. So note that the name of this, if I select rename, the name of this is tractor_tire. That name needs to exactly match this string input for geometry name. That's how PM FlexTire communicates to EDEM and identifies which geometry elements are the FlexTire and which geometry elements are associated with all of these other input files. So I'll close the tractor tire.flextire, and then to enable the simulation with PM FlexTire, it's as simple as enabling this FlexTire option. That may not be visible in your EDEM session. If not, you come up to the Tools, Options, and under Additional Components, you need to check Enable FlexTire, so that shows up. Then we'll point to the FlexTire file. In this case, I've already updated the FlexTire file that's in the same directory, and I will specify a pressure of 35,000 pascals. And this simulation would then be ready to run. In the physics, note that the particle limits have been disabled, so the particle bed will move now with the tire, and that's important because I'm going to use a 20% Rayleigh time step to solve the simulation. 20% Rayleigh time step is not only required for the particles, but also for the flexible model of PM FlexTire. It requires a relatively small time step. If you stick with that 20% Rayleigh time step, based on the particle size, you'll have a reasonable or an accurate resolution of the flexible tire. Now, one other thing that I often do before I execute an EDEM simulation with PM FlexTire is check out the mesh. For this, I've downloaded and installed the free version of MeshLab 2023.1, and we can import the .off files that were generated and the .obj file that was generated from the execution of that batch mesh file. So if I import all of these components, I'm just going to turn off the tire itself. Those are the volume elements. And then we'll go one by one through the individual elements. So the tire bead appropriately is 2 rings of elements around where the rim would be touching. If I turn the belt on, we can see that we've got a continuous surface from one side to the other that is the nodes, or sorry, I should say the surfaces, the triangular elements associated with the belt. The inside, sorry, the sidewall, sorry, no, that was right. The inside is the area that will experience the air pressure, and I'll turn off the other elements and just leave the inside on. So all of the inside surfaces of these triangular elements would be the surfaces that are exposed to that 35,000 Pascal pressure. And then we've got the sidewall, separate elements make up the sidewall of the tire. So if we leave the inside off and turn on belt, bead, you can see that those are all unique zones of the tire. Turn the inside back on, and also the volume elements of the tractor tire. Now in this case, you can see the surface elements of the lugs align well with the rest of the mesh, so everything looks appropriate. Another thing that I should point out that we skipped over previously is to take a look at the tractor_tire.ftx. That this file is pointed to from the FlexTire file. I've also updated it with the appropriate units in the unit block, and in here is where you would specify the parameters of mass, center of mass, and moments of inertia for your rim and tire, and some global parameters like your rim radius, width, Young's modulus, Poisson ratio, damping ratio, and then on a per element basis for your inner liner, belt, and sidewall, the Young's modulus or E modulus, Poisson ratio, thickness, the E modulus XXYY, G mod, Poisson ratio, XXYYZZ, material type, the start and end air pressure, and the geometry, tires, the location of the step tire for the tire and the rim, and the axis of rotation. So that file also needs to be updated because it's used in the FlexTire as well. Close that. Now we can switch over to EDEM and start to run the simulation. To run the simulation, we'll just switch over and enter calculate. Now, off the start of the simulation, you should see a relatively slow progression. As the simulation runs, you should see a relatively large increase in the rate at which it solves. One thing I did want to point out before I start the execution of this simulation, or what I should have pointed out before I started the execution of this simulation, is that the tire mass may need to be updated. I'd set that to 550 kilograms, and I've manually updated the position of the center of mass to be 1200 millimeters in the Z and 0 in the X and Y. Also note that I rewound the simulation to 0 and saved it to restart the simulation. You cannot restart a PM FlexTire simulation from a point other than 0. But now that we've updated the total mass and the position of the center of mass, you can see that the simulation runs without air.